Thank you very much to the Institute for Advanced Study for sponsoring this week. So what I'm going to do today is basically explain what we're trying to do this week. And the key topic is scalar curvature and convergence. I'll try to give you a little bit of history about curvature and convergence and the various notions of convergence we're going to talk about. I'll define them very quickly. So the main idea is to get you introduced to what's going on this week. We have a schedule of talks this week. Let me just sort of give a little introduction to this while people are still coming in. We'll have discussions at lunch and tea every day. This is the only public talk today. On Tuesday, Misha Gromov will talk at 1:30. Then Rick Shane will speak at 3 p.m. right in this room. On Wednesday, Lan Xuan Huang will speak at 9:30. Is this correct? Yes. Yes, at 9. Yeah, Lan Xuan Huang will speak at 9:30. Raquel Perales will speak at 11 a.m. in here. And then we are moving over to Princeton for the Wednesday afternoon. What you can do is you can catch a jitney from, there's a jitney that stops right near Fold Hall. So at lunchtime, at the end of lunch, we'll be running over to the jitney. And there's plenty of time to walk across Princeton campus after you get there by the little jitney bus. And at that point, we'll have a talk by Miao, by Gofeng Wei, and Otis Chodesh, who's representing Michael Eichmeyer, who could not make it. So it was their joint work anyway. So Wednesday afternoon is all in Fine Hall at Princeton, and then you guys can all head back for Wednesday evening. There's actually mathematical discussions by Gromov, which is unrelated to this conference. And then on Thursday, Bernard Hanke will speak at 1:30 p.m. right in here, and that's the only talk on Thursday, but we can have discussions at lunch and tea. And Friday we have 3 talks, Alan, Portuguese, and Laxian, and then there'll be discussions in here. And what will happen on Thursday is, during the week, a few of us will be devising conjectures and what would be actually feasible for people to work on at various levels. And at the final discussions on Friday, we'll be in here and we'll divide up teams of people who would like to work together on some of these projects. But right now we're trying to spend the week trying to solidify exactly what the conjectures are. All right, so let me just start with a little history. So let's begin with sectional curvature, just because it's the strongest notion. For sectional curvature, if you have, we have the famous topological comparison theorem. Which says that if you have a triangle, if your manifold has sectional greater than or equal to 0, that means your triangles are fat compared to Euclidean space with the same lengths. So if this side matches this one, this length matches this one, this third side matches this third side, then these this as you move along the curve C of t, and if you move along the curve C tilde t here in the comparison space, that the length of this curve, or the distance from this top point to C tilde of t, is bigger over here. So distance C of t is bigger than the distance in Euclidean space between P tilde C tilde. This is an Euclidean, this is an M. So that's the topological comparison theorem, and it leads naturally to a generalized notion of sectional curvature. So we have generalized sectional curvature would just be to say that you have a metric space with geodesics that satisfies this property. So this leads to Alexandrov spaces that's a generalized notion of the sectional curvature manifolds. They're Alexandrov spaces. They satisfy this condition. These spaces have a compactness theorem. So if MJs have, so let me write this. So we have MJs, if they Gromov-Hausdorff converge to some M infinity, and these guys have the sectional, then this guy has the Alexandrov curvature. And so this is a generalized notion of what it is to have sectional curvature, non-negative. And also there's a compactness theorem, Gromov's compactness theorem. And this Gromov's compactness theorem guarantees that if you have a sequence of MJs with sectional greater than or equal to 0, a subsequence converges. So if sectional greater than or equal to 0 and diameter less than or equal to d for each one of these j's, then a subsequence mjk converges in the Gromov-Hausdorff sense to m infinity, who is Alexander, with curvature bounded below. All right, so that's the general idea of what happened with sectional curvature. It's actually interesting to note that m infinity is actually rectifiable. Which was proven by Barago-Gromov-Perelman. So even though initially, when defining what it means to have Gromov-Hausdorff convergence, there's nothing to talk about rectifiability, they boost the regularity later and are able to prove that these Alexandrov spaces are rectifiable. Now, let me just give a slight reference over here to what is Gromov-Hausdorff convergence. Gromov-Hausdorff convergence is built upon a distance between Riemannian manifolds. Both of them are compact. And you say that the Gromov-Hausdorff distance is the infimum of the Hausdorff distance between their images. So you take the two manifolds, you put them into one space together. You take an infimum over all compact metric spaces Z. So we're inside Z. And distance preserving maps from phi I from mi to z. So this is saying take your two Riemannian manifolds, put them into a same place together, and then measure the Hausdorff distance between them. How far apart? You can put them together in all possible ways, but keep it as distance preserving maps, which prevents crumpling one space. So here, this distance preserving means that the distances after inside Z are the same as the distances before. So you're not allowed to crumple either space. The spaces are rigidly mapped into a common compact metric space, and then you measure the distance between them using the Hausdorff distance, which is an infimum of radii such that the one image is sitting in a tubular radius of the other, and the tubular radius of the first contains the other. So basically, the Hausdorff distance between these two guys would be really rather large because it has this pointy part. So this is the notion of convergence that works very well for sectional curvature. If you have a sequence of Riemannian manifolds that converge in the Gromov-Hausdorff sense, you'll notice that the M2 could have just been a metric space. There's nothing about Riemannian geometry in that definition. So he converges to a metric space, and then you can check that geodesics go to geodesics, and we end up having the Toponaga comparison theorem persisting in limit. Yes?
What does rectifiable?
Rectifiable means that there is a countable collection of charts. It's a fancier name than this. I wrote it short. There's a countable collection of charts that are by Lipschitz from Borel sets into the space, and they cover almost the whole space in the sense of Hausdorff measure. So it's pretty nice. All right, so now comes Ricci curvature. For Ricci curvature, there's the Bishop volume comparison theorem. And we'll use the Bishop-Gromov version. And I know I'm very oversimplifying things, but this is a quick survey. So this theorem says that inside M, if you have a ball inside a ball, and then in Euclidean space of the same dimension, you have a ball inside a ball, that the volume of the smaller ball divided by the volume of the larger ball, this is in the manifold, is bigger or equal to the volume in Euclidean space of a ball of radius r, the volume in Euclidean space of a ball of radius big R. This is dimension M. So we have comparisons for volumes of balls.
So you assume positive.
This is Ricci greater equal to 0. I'm making life all easy, so let's just make sectional here. Of course, all our questions involve other lower bounds, but just to write things as simply as possible, we'll just do Ricci greater equal to 0 here. Okay, so yeah.
It can be big balls or not only small balls.
This is for all r's that are less than r. Yeah. So this is basically saying that this inner ball is fatter than expected. It's the same idea as this inner geodesic is fatter than expected. So you can think of this as being the same kind of theme. This inner ball is too big compared to the outer ball. All right, so we have this volume ratio, and this leads to the idea that, okay, so we have Grommel's compactness theorem still holds. Only requires Ricci greater than or equal to 0, diameter less than or equal to d, and we get MJ's subsequence GH's to M infinity. Now we have a problem because M infinity, if you use the Gromov-Hausdorff distance, only has notions of distances. This is for metric spaces, but not for measures, and you need a notion of measures in order to talk about volume ratios. So we actually, Cheeger-Colding prove and Colding that you get a measured Gromov-Hausdorff limit. So let's just do the simplest version, which is non-collapsing case, which is to say that volumes are bounded below. Then we can say that the MJ's measure GH converge to M infinity. And now M infinity is a metric measure space. With the Hausdorff measure. So it has a Hausdorff measure. Let me just write Hausdorff measure up here. So you now have that the balls in here, the volumes of balls in here converge to volumes of balls over here. There's also collapsing versions. I'm just writing the very simple, very fast thing. So once you have measured GH convergence, now you can talk about this. You just use Hausdorff measure. So this is fine. Instead of volume, we write Hausdorff measure. And indeed, they prove that this condition, this is true with Bishop. Comparison for the Hausdorff measures. Okay, so all of that was proven. And then that wasn't enough. There was actually more, because you really want to prove this Bishop-Gromov volume comparison theorem is not the only important theorem for manifolds with non-negative Ricci, and it doesn't really capture all the power. So there's also actually a splitting theorem which says that if you have a line inside your space and you have non-negative Ricci, then the entire manifold splits isometrically. And this splitting theorem also holds on M infinity. And using that the splitting theorem also holds, they actually get M infinity is rectifiable and much more. And more, like tangent spaces are Euclidean almost everywhere and things like this. So you have this generalized class of spaces, and now, okay, here we had a complete generalized class of spaces, which was the Alexandra spaces, and all they needed was this comparison. But over here, we don't have this. This isn't enough just to say that the Bishop-Gromov volume comparison holds. Doesn't give you enough strength on the limit spaces. So they developed notions, Lott, Villani, and Stern. Developed a notion called the CD spaces, which satisfies some sort of volume entropy condition. And then there's Ambrosio Gigli Savare, introduced. So these spaces have this happening, but they are not strong enough to cause the splitting theorem to hold. But the Ambrosio Gigli Savare RCD spaces, they also have splitting, and this condition proven as a consequence of their definition. Okay, so you have in this setting, compactness theorems, you have a nice notion of convergence. The best notion is this one. You have properties that persist on the limit. And then there's very complex definitions of CD spaces and RCD spaces, which imply our favorite theorems for non-negative Ricci. So if you're on a CD space, you have this volume comparison. If you're in an RCD space, you have this plus the splitting as consequences. Yes? Yeah, the splitting theorem, I don't have room to write it here, but it says that if you actually have a line, which is distance minimizing on every subsegment, then the manifold itself splits isometrically into R cross a manifold of one dimension lower. That's if it's complete non-compact. It's a very important theorem, and they use that locally. Cheeger Colding prove it. They use it locally for showing that tangent spaces are nice and Euclidean. Of almost everywhere, not all the time. They can still have corners. All right, so now the question are, what notion of convergence works? Should we use for scalar here? What notion of convergence is best? There was Gromov-Hausdorff. Here was measured Gromov-Hausdorff. What theorems, what properties or theorems should hold on the limit spaces? On the limit spaces. And what should our generalized spaces be? And do we have a compactness theorem? All right, so that's the oldest question. A lot of this has sort of already been a little bit answered. And notice that we don't necessarily expect that there should be only one answer, because for generalizing Ricci curvature, there were two very nice candidates. This one had some of the conditions, and this one had even more. So we might very well do something similar with the scalar. We might make a generalized notion of the space, a first round generalization that's good enough to have some of the properties of scalar curvature, and then a second round stronger generalization that has everything. And there are many more names over there, and this has been going on for decades, so I expect this also can go on for a few decades, if not more. All right, so let's just start with the biggest challenge about scalar curvature, which is that, notice that in Topinogov comparison theorem, this one, there was Gromov-Hausdorff convergence. And this one also had Gromov's compactness, so we had Gromov-Hausdorff convergence. But the very first thing that happens when you study manifolds with scalar curvature, and these are three-dimensional spheres with non-negative scalar curvature, so they have scalar greater than or equal to 0, and their volumes are bounded below uniformly. And their volumes are also bounded above. In fact, their volumes are going to a sphere. Diameter is bounded above. How good could these spaces be? I mean, this is a lot of nice conditions on them, and yet they have these sort of well shapes. So let me describe the well shape a little bit, because it's a crucial problem with scalar curvature. These wells, these are three-dimensional. So the sphere parts of the wells, these are spheres. They're little spheres. And you see what looks like negative curvature here is countered by the positive curvature of the sphere, so that when you sum it over, it becomes greater than or equal to 0. So you've got these sequences of spaces. Every one of them has scalar non-negative, and they're developing more and more wells. Now, that makes a problem because actually Gromov proved that if you have a sequence converging in the Gromov-Hausdorff sense, then in fact, they could all embed into a common compact metric space Z and have this. That's a major theorem of his. That's not obvious. Hi, you want to come sit in front? Nothing you don't know.
Maybe we should include interferity radius or something like that.
Yeah, but we don't want to, right? We didn't do it for the other spaces, so why would we do it here? Yeah, okay. So we don't want to, we have this situation. We don't know what notion of convergence would work, but there's definitely no GH limits, even for a subsequence, because there's no way this entire sequence could fit inside a compact Riemannian manifold, because the number of balls that are disjoint is going to infinity. Okay, so if you take a ball of, say, half the radius of the depth, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 of them, and they go up. So there's no Gromov-Hausdorff limit. And Illman presented this example. He said maybe there should be some sort of a weak limit. And so that led to the intrinsic flat distance. So the intrinsic flat distance I defined with Stefan Wenger is between pre-compact oriented manifolds, and it's based on the flat distance of Federer-Fleming. And the idea is that you don't really need distances. You want something like this to be small, not so large just because it has a little tiny tip there. So we want to imitate the flat distance of Federer-Fleming, which was used for submanifolds in Euclidean space. And you want to say, okay, actually this distance ought to be the infimum of the flat distances between the images. So this is the images using current notation. As in Federer. Okay, so we push them forward, we view them as currents, and we say, what is the flat distance between them? Again, we use distance-preserving maps, just like Gromov did, but we only require Z to be complete because we don't want to have issues of having to force them all in a compact space. And then we say we measure the flat distance between their images, and the flat distance is basically the same one as in Federer-Fleming, but this is like a weighted volume. It's the sum of the volume of something of the same dimension used to close it up as a cycle, plus the volume of something one dimension higher that fills it in. So we go over all possible a's and b's such that the integration of the one minus the other is equal to the integral of a plus boundary b. And this is all made rigorous using Ambrosio-Kirchheim. So Ambrosio-Kirchheim defined currents on metric spaces. The flat distance between the currents is the sum of the weighted volumes of the possible fillings in. So if T1 is one current and T2 is another current, you close it up with an A to make a cycle, and then you fill it in with something. And these things are also currents, so that's why it's a weighted volume of sorts. Okay, so now the idea, this is based on when we were solving the plateau problem in the 1950s. The same kind of images happened for the plateau problem. You were trying to find the smallest area filling for a disk, and you take a sequence of surfaces whose area is going to the disk, and they could develop all these kind of 2B things too. So this is just making an intrinsic version. Actually, Gromov called this the intrinsic Hausdorff distance, so we were imitating the same idea. It's an infimum over all pushes.
They use prime as a way, by somebody in the 70s. I keep forgetting some mathematical physicists.
Oh, who introduced the Gromov-Hausdorff?
Right.
Yeah. Okay.
I didn't know that, but this came up. And you can
Okay.
in Wikipedia now.
Darn. Okay, I should have put his name. Okay. Okay. All right, so we have this notion, and now with respect to this notion, this actually has a flat limit. So we use big fancy F and this actually, all the wells disappear. Okay, so that's what we want. So now it becomes possible that the answer to the first question is maybe the flat convergence. Or a related one, the volume flat convergence. So let me explain. The volume flat convergence is the same sort of idea as the measured Gromov-Hausdorff. The measured Gromov-Hausdorff makes that the volumes of the balls converge. If you have only flat convergence, there's no reason for volumes of balls to converge. Okay, so the volume preserving Hausdorff flat distance is one which says that actually not only is the distance between them, okay, so the volume flat distance says take the flat distance plus the difference between the volumes of the whole spaces. And if you do that, then you get volumes of balls to converge. So that's a stronger notion that gives us better power. For example, if you have volume preserving flat convergence, then Portuguese has shown that the eigenvalues are upper semi-continuous for the Laplacian. So there's some nice properties if you have volume flat convergence.
Sorry, I didn't quite get the difference at the technical level between these two nodes.
So okay, so if mj's flat to m infinity, then the limit as j goes to infinity of the volumes of any balls in the spaces is bigger or equal to the volume of a limit ball. Almost every r. Okay, and p infinity is in m infinity. So if you have this flat convergence, then you can find points, and the volume will be lower semi-continuous, and if mj vf to m infinity, then the limits are equal. Almost every r. This is a theorem. The definition is just that. The definition is mj flat to m infinity plus and volume mj. The whole mj goes to volume m infinity. As a consequence of that, you get the volumes of balls to converge. So let me just clarify one point. When I say, so here's your p infinity sitting in your limit space, we find pj's that go there. So here's a p3, p2, 1. Okay, but it's possible. Okay, so that's like the ones we're talking about here, that the volumes of the balls converge. But notice that points can disappear. So if I took q1 here, q2, q3, the qj's disappear. There's no limit. Okay, in Gromov-Hausdorff convergence, you could have a subsequence of them converging. But here we don't have that. Okay, so with this sort of things to keep in mind. All right, so at this point, the next question is, what theorems should hold in the limit spaces? So one of the main theorems that should hold in the limit spaces is what's called the torus. Let me just bring this down. I have never put lower injectivity radius bounds on anything. It almost undoes like the beauty. Yes, but it undoes the beauty of all the work that was done for Sectional and Ricci. Okay. I mean, so why would we add a condition they didn't have? Okay. So anyway, So the scalar torus theorem Shane Yao, Gromov Lawson. So this theorem says that if M has scalar greater than equal to 0 and is homeomorphic to a torus, then MM is isometric to a flat torus. That's one of the most important theorems for scalar curvature. So when I say what theorem should hold in the limit space, we kind of like that this theorem would actually hold on the limit space. Isometric. There's an isometry. Okay, so distance preserving map, that's surjective. Okay. So this is one of the theorems that we might want to hold on the limit space. Another one would be maybe the positive mass theorem. Now, Witten has a spinor proof. That's another one of the key theorems that you might want to hold for limits of manifolds with non-negative scalar. And so that sort of is what we're getting into tomorrow. Misha Gromov will speak about what sort of properties he would like the limit space to have, including like polyhedral properties, things like this. And Professor Rick Shane will speak about positive mass theorem, the latest all-dimensional case of the positive mass theorem. So you'll see that these more about this theorem tomorrow. But I just wanted to say one thing is we would like this theorem to hold on the limit space. So what do you mean by that? And what should our generalized spaces be? That would mean that they should have enough properties on them to imply these theorems on the limit space directly. And then we should say, do we get a compactness theorem? So for the compactness part, we already sort of have a compactness theorem. This is for Wenger. Prove that if MJ's M have volume less than or equal to V naught and diameter less than or equal to D naught, and he has let's assume no boundary for this one, then a subsequence converges in the flat sense to some M infinity, which is an integral current space. It's a rectifiable metric space, or it's nothing, or zero space. These rectifiable metric spaces, that's the full class of spaces we defined over here. So we didn't actually require that they be precompact oriented manifolds. We actually said that they were things called integral current spaces. Which are special rectifiable oriented metric spaces with weights. So that was the class of spaces we talked about, and his limit spaces in his compactness theorem are for these integral current spaces. Integral current spaces also include the zero space, which happens, for example, if the volumes of the manifolds go to 0. Okay, this is a very quick introduction. So he has a compactness theorem. So immediately you could apply this to sequences of there's no scalar curvature here. Okay? So if we add scalar, what about the limits? extra do we gain for M infinity? What properties would you also gain for M infinity if you add scalar curvature to Wenger's compactness theorem? It's already rectifiable, so we already have that condition that was proven for the Alexandrov spaces and the Ricci limits, that they were rectifiable. And actually, just as a side, for non-negative sectional curvature, the intrinsic flat limit agrees with the Gromov-Hausdorff limit. Okay, so in that case, that's been proven by Pross and a few others. And for Ricci bounded below, Medvedev in Portuguese and Wenger and I proved for Ricci bounded below, the intrinsic flat and Gromov-Hausdorff limit agree. So this is generalized the pre-existing situation. But what happens if we say scalar j is greater than or equal to 0? One natural thing to try to prove is, before trying to prove, oh, we have this generalized notion of a space that's non-negative scalar, and it therefore has these two theorems on this generalized space, would be interesting to check, does this hold on a limit achieved this way? Okay, so do our theorems hold on, not ours, but whatever, hold on limits M infinity like these guys. So one way to phrase this, it would be a conjecture that if mj have scalar j greater than or equal to negative 1 over j, and let's say volume bounded above and diameter bounded above, and I'm deliberately skipping a line here, okay? And mj's, okay, under this condition, we can already apply Wenger's compactness, so we have a subsequence. So we have the mjk's have gone to M infinity, and M infinity is homeomorphic to a torus. And let's just stick to 3 dimensions for this theorem, because this is a conjecture, and who wants to be too bold, right? Okay, so stick to 3. Is M infinity a flat torus? As in, this is actually smooth and flat. All right, so that's a conjecture. You could sort of give this conjecture to Gromov. I'll write that here. So, of course, hidden in here is that we need something to avoid just ordinary flat tori collapsing to nothing. That's always a possibility. So we need some sort of n non-collapsing condition. And the sense of non-collapsing is something that we need to work on. What is it that we're going to use for non-collapsing? And I resist using injectivity radius because the injectivity radius wasn't used for the others. So for Ricci curvature, just a volume lower bound was enough to have the non-collapsing. Okay, so to understand this, I'm going to put up some pictures now for this conjecture in particular. So it takes a little while to draw up these pictures, so let me just start with the very simplest sequence. You have a sequence of manifolds, and these guys are even converging smoothly to this flat torus here. And what I've done is I've made sure each one has a ball inside it that is isometric to a ball in a constant curvature sphere. So these green balls are all isometric to balls in constant curvature sphere, and this limit of them is isometric to a ball in Euclidean space. These are 3-dimensional manifolds, and they're all tori, and this limit is a torus. it's homeomorphic to a torus. It looks like a flat torus. And this picture looks fine. And here's the conjecture. I already wrote it down here. I don't know why I wrote it up there. Okay, so now, what could happen that could lead to trouble? So let's add some more interesting things happening here. If we put in these wells, because in the Illman example, you could attach wells to spheres. So we can put in more of them. And more of them. So there's no GH limit, but this sequence, this particular sequence seems to converge in the flat sense to the same thing. So it's okay. So if we add wells, with wells, we get flat, but no GH. For this particular sequence, this is just an example. It's not a proof of the theorem in general. All right, well, what else could happen? Maybe not wells. Maybe what could happen is bubbling. So we could have a bubble here. And the bubble could get thinner, but just as big. And then here the bubble is really thin. And then the limit is a flat T2 with a bubble attached. At a point. And that is actually the Gromov-Hausdorff limit of this space and the flat limit. So that's kind of troublesome. So one would kind of like to make up a non-collapsing condition that avoids bubbling. And so one possible way to make a non-collapsing condition that works is we could require that the area, the minimum area, is bigger than the sum A naught greater than 0. Let me define min A. So min A of a manifold, of a three-dimensional manifold, is the infimum of the area of any minimal surface, sigma 2 minimal in M3. Okay, so that's a natural thing. This is already studied a lot for manifolds with scalar curvature that are non-negative. Conditions on this min A are used in, and slight revisions of this min A are used in Brendel, Eichmeyer, Neves. There's somebody else, but anyway, where they're saying if it's RP3 that it's going to be forced to be a standard RP3. They have a sort of not torus rigidity, but RP3 rigidity theorem, and they have the min A approaching the extreme condition. So this min A has been used elsewhere. Also note that in the Shane-Yao proofs of scalar torus rigidity and positive mass theorems, everything involves minimal surfaces. So the idea of understanding minimal surfaces in the three-dimensional case seems to be a crucial notion. If we add that condition, then we have all these, we can't have this bubbling because the bubbles have smaller and smaller minimal surfaces in the neck. So this would prevent bubbling. This also prevents tori collapsing because if there's a torus that's getting thinner, the cross-sectional area will go to 0. So this is a good collapsing condition to handle both tori collapsing and bubbling. All right, so that's the next picture. So this is the conjecture. You can add this min condition, but if we're going to add that condition, maybe we ought to also add it here. To gain more for M infinity. All right, so then there's one last concern, which is that you could have something called sewing, which I don't have time to present, which is even worse than bubbling. And it means that you take lots of little tiny, tiny tubes and you can pull them tight, and so the limit space is very strange looking, and that's also prevented by min A. So not only does it prevent bubbling, but it also prevents something called sewing. Something called sewing, which I can show anyone anytime.
So if you add this condition in arbitrary dimensions, what kind of...
No, that's something we'll have to discuss this week. Especially since Shane will be talking about positive mass theorem in all dimensions, we can see what's crucial. I don't know if it should be area of codimension minimal surface and then the area of the smallest minimal surface, codimension 1, minimal surface in that minimal surface after it's already been conformally changed, or it could be very complicated. But in 3 dimensions, there's a one-step process that only requires a single minimal surface. So it's easier to state it here. A higher dimensional version would be hard to state if you want to imitate Shane Yao kind of things. So that's something we can discuss, higher dimensional issues. Higher dimensional examples is something to discuss. And now let me just, since it's really almost time's up, let me just quickly go through what's happening this week. Lanswan Huang is going to talk about the corresponding sort of theorem of this style for the positive mass theorem and results that have been done so far. So that's been done it's actually been proven in some special cases already. So she'll go over that. And Raquel Perales will talk about one setting in which this conjecture has been proven already with an extra hypothesis. And also Brian Allen on Friday will talk about another setting of where this conjecture has been proven already. So, but they're special cases, but it's nice testing them. Peng Zim Yao is going to talk about volume properties of manifolds with scalar curvature, non-negative, that we might want to hold in the limit, or we might use it to help control the limit. And Otis Chodash will speak on his work with Michael Eichmeyer about sort of isoperimetric properties. This has not appeared yet on the archive, so that's very cutting edge. Hanke will talk about flexibility with scalar greater than equal to 0. And Portuguese and Laxian will talk about various properties of intrinsic flat convergence. So theorems about intrinsic flat convergence that might be useful or have been useful already towards proving the special cases. So I'll stop here. Thank you. So, questions?
Shall I have some words? Okay. Are there any questions or remarks?
Yeah.
So for this conjecture that you have there,
Yeah.
do you actually have a counterexample where you don't have the non-collapsing condition, but the limit is now homeomorphic to a torus? Do you have a counterexample?
Yes, that's the sewing. So the way to get that counterexample, yeah, this is the sewing. It's joint with my student Jorge Basilio, and so what you do is you get a limit. The limit space is, you can make an entire little purple ball in here collapse to a point. So that the limit space is a flat torus with the region that's identified to a point. So it's not a flat torus anymore, it is homeomorphic to a torus. And this is created, the sewing process is a matter of taking, instead of wells or bubbling, you take advantage again of this basic shape at the beginning of a bubble, these necks, and you attach them at another spot. And then here you attach them at more spots. And here you attach them at more places. And you attach them in many, many combinations. And that sort of makes it a shrinking distance. Anything in the purple ball will be arbitrarily close to anything else via these sort of space tunnels, you know, like gates, stargates between everything. And it shrinks it to a single point. So that's homeomorphic to a flat torus, but it's not a flat torus. And you can do this worse, but that's the easiest. Thanks.
Christina, are you primarily interested in compact manifolds here? Or?
The positive mass theorem is non-compact story.
Right, yeah.
So we're going to talk about that, yes. This is for simplification. For the first talk, I said compact.
No, I say this because I will also on Thursday talk about some applications of index theory to non-compact manifolds.
Great. So we're going to do non-compact here, and we're going to do Shane's going to do non-compact, and Huang is definitely doing non-compact. Yeah.
Okay.
And she's doing definitely higher dimensions too. Are you doing higher dimensions? Or 3?
What dimension do you like? No, I should.
No, you have a long talk. So
it's the point. So the index theory applies to
all the dimensions, yeah.
Yes.
Again, the 3 dimensions was partly for simplicity. I think, yep.
Yeah,
Okay.
thank you.
Thank you.